Okay, so today we'll look at eigenvalues and eigenvectors. Outline, we'll define what eigenvalues and eigenvectors are, and then characteristic polynomial of a matrix, uh, then multiplicity of eigenvalues, and we'll see what defective and non-defective matrices are. And now I'll tell you upfront that throughout this course, we will assume, unless otherwise stated, that the matrix is non-defective. You don't know what non-defective and defective matrices are yet, but we will be dealing entirely with non-defective matrix henceforth. Triangular matrices, determinants from eigenvalues, Hermitian and symmetric matrices, similarity transformations, shifts, and inverses of matrices. Okay, so given a n by n square matrix A, let V be a vector, n by 1 vector, and lambda be a scalar, such that AV equals lambda V, and V is not a zero vector. AV equals lambda V. Then all solutions V and lambda are eigenpairs. So the n by 1 vector V is called a right eigenvector, or simply an eigenvector, and the scalar is the corresponding right eigenvalue, or the eigenvalue. Eigenvectors are usually normalized so that the norm of V equals 1. This is not always the case, but the preferred method of writing eigenvectors. Okay? And eigenvalues and eigenvectors always occur in pairs. So you'll have lambda and V occurring in pairs, and we will refer to them as eigenpairs. The n by n matrix A has up to n eigenvalues. Now, if we sort the eigenvalues numerically in terms of their actual, their absolute values, their magnitudes, then we usually index them like this. Lambda 1 is the eigenvalue which has the largest numerical value, and the next largest one is lambda 2, and so on. And if we place the corresponding eigenvector, then lambda 1 V1 is an eigenpair, lambda 2 V2 is another eigenpair, lambda 3 V3 is another eigenpair, and so on. The spectrum of the matrix is the set of eigenvalues. And the spectral radius of the matrix, rho of A, is max of lambda I. And if we sort them in this order, we index them in this order. So lambda 1 is the one which is numerically the largest eigenvalue. Then absolute value of lambda 1 will be the spectrum of the, the spectral radius of the matrix. Now suppose V transpose A equals lambda V transpose. Then V and lambda satisfying this equation, the solutions of this equation are called the left eigenvalues and left eigenvectors. But everywhere in this course, we will be dealing with right eigenvalues and right eigenvectors, and we shall simply call them eigenvalues and eigenvectors. Okay. The characteristic polynomial. So we're considering an eigenvalue and an eigenvector, lambda and V, so that AV equals lambda V. Whence lambda V minus AV equals 0. This is actually vector 0. You can bold it out. Implies lambda I minus A, I'm factoring out V. So lambda I minus A times V equals 0. Remember this I, because this is a matrix A. and lambda is just a scalar, so you have to include this identity matrix I here. So lambda I minus A times V equals 0. Now, this is a matrix. Lambda I minus A is a matrix, and V is a non-zero vector, correct? So if you are multiplying a matrix with a non-zero vector, then what can you say? This matrix must be singular, right? Because a matrix times a vector is basically the weighted sum of the columns of the matrix, right? And if the weighted sum of the columns of this matrix A, the way it's being in V, the elements of V, if this weighted sum is equal to 0, which means that any one column can be represented as a linear combination of all the other columns of the matrix, whence the columns are not linearly independent. Whence this matrix, if this matrix A times a non-zero vector V is 0, then we can conclude that the matrix is singular. It must be singular, its determinant must be 0. So now the determinant contains this lambda, so it will be some polynomial in lambda, P of lambda. Okay, and this polynomial, which is determinant of lambda I minus A, is called the characteristic polynomial. The eigenvalues of A are the roots of this characteristic polynomial. And let's take a very small example. We have this matrix A, 1, 2, 2, 1. Let's find its characteristic polynomial and then the eigenvalues and eigenvectors. So lambda I minus A is equal to lambda times the identity matrix minus A, which is this. Lambda minus 1, negative 2, lambda minus 1. The determinant is this determinant here, lambda minus 1, negative 2, lambda minus 1, this determinant, which is lambda minus 1 squared minus of negative 2 squared, which is this, which simplifies to lambda squared minus twice lambda minus 3. So this is the characteristic polynomial. And for this matrix to be singular, its determinant must be 0, whence this must be 0. So this is the characteristic polynomial. I jumped a little ahead. So this is the characteristic polynomial of the matrix. And since this is singular, therefore the solutions, it must be singular, right? That hence lambda minus 3 times lambda plus 1 must be 0. That gives two values. Lambda 1 equals 3 and lambda 2 equals negative 1. So these are the two eigenvalues of the matrix A. Any questions?
No.
No. So the eigenvalues are the roots of the characteristic polynomial. Now let's find the corresponding eigenvectors. For lambda 1 equals 3, and then for lambda 2 equals 1, we'll find V1 and V2. Okay, so what's V1 for lambda 1 equals 3? Let's say V1 is AB for some scalars A and B. Now lambda 1I minus A times V1 must be equal to 0, right? Whence I plug in the values of A, 1, 2, 2, 1, and I, the identity matrix. So this lambda 1 minus A becomes equal to lambda 1 minus 1, negative 2, lambda 1 minus 1. And this V1 is AB, so this must be equal to 0. And Lambda 1 is 3. So what do I get? This becomes 2, right? Lambda 1 is 3, so lambda 1 minus 1 is 2. So 2 times A1 minus 2 times B. This is, I said A1, it's A, and this is B. So 2A minus 2B should be equal to 0. Minus 2 times A, since lambda 1 is 3, so this is 2. So minus 2 times A plus 2 times B should also be equal to 0. Hence, the solution is A equals B. Okay, and we can choose whatever value of A we want. Okay, and so the B1 can have any of these forms. It can be 1, 1, -3, -3, 0.2, 0.2, as long as A equals B. But we want to usually express the eigenvector as a unit vector. So we want the L2 norm of B1 to be equal to 1. So we let A equals B equals 1 over square root of 2. Therefore, V1 is 1 over square root of 2 times 1, 1. Now, we could have easily put a negative sign here too. So the V1 could have been -1 over square root of 2 times 1, 1 as well. And both would have served the same purpose. So remember, the eigenvectors are simply directions. If V is an eigenvector, then -V is an eigenvector. 2 times of V is also an eigenvector, although it's not normalized. 25 times V, -5 times V, they're all eigenvectors. Okay, so this is V1. Now let's go to lambda 2 equals -1 and find that eigenvector V2. This is what we have to solve. 2, 2, 2, 2, AB equals 0, where V2 is AB. And the solution is A equals -B. So our eigenvector V2 normalized is 1 over square root of 2, 1, -1. It could have been -1 and 1, 2. Doesn't make a difference. Thus, the eigenpairs of A are 3 and 1 over square root of 2, 1, 1, and -1, 1 over square root of 2, 1, minus 1. These are our eigenpairs of A. For a triangular matrix, for a lower triangular matrix L, the diagonal elements Lii are the eigenvalues. Likewise, for an upper triangular matrix, again, the diagonal elements Uii are the eigenvalues. What are the eigenvalues of this matrix A here? It's a lower triangular matrix, right? And so the diagonal elements, -j, 2, and 1 are the eigenvalues. And if we sort them so that numerically, the largest one appears first. So lambda 1 is 2, and lambda 2 is -j, lambda 3 is 1. Well, we could have made this 1 and this -j2. Doesn't matter. Now, given an n by n square matrix A, the characteristic polynomial will be a polynomial of degree n, right? So the highest degree will be lambda to the power of n. We saw that for a square matrix of dimension 2 in the example, the characteristic polynomial here was this, right? Was a quadratic. That's because this was a 2 by 2 matrix. And in general, for a n by n matrix, the characteristic polynomial will be of degree n. Lambda to the power of n will be the highest degree. Okay? So this is the general form of the characteristic polynomial. And we can factorize it out in this manner. Lambda minus lambda 1, lambda minus lambda 2, all the way until lambda minus lambda n. Okay, now here I am applying unique indices to the eigenvalues. So I have lambda 1 and lambda 2 all the way to lambda n. I can also follow non-unique indexing. Okay, so this is two different way of applying indexes to the eigenvalues. It's possible that lambda 1 and lambda could be equal, right? So I could have written lambda minus lambda 1 squared instead of lambda minus lambda 1 and lambda minus lambda 2. So if I use non-unique indices, then the characteristic polynomial can be expressed as lambda minus lambda 1 to the power of mu 1. Mu 1 could be 1, 2, 3. Then lambda minus lambda 2 to the power of mu 2, and so on. Or P of lambda equals the product of lambda minus lambda I to the mu I. This I does not go all the way up to n as in this case, because we are using non-unique indices. Multiplicity of eigenvalues. Mu of lambda I is the algebraic multiplicity, which is simply the number of times lambda I is a root of P of lambda, the characteristic polynomial. So lambda I is an eigenvalue, and its multiplicity is mu I. Multiplicity can be 1, 2, 3, whatever. Summation mu I should be equal to n, because the highest degree is n. Geometric multiplicity. Now, suppose we have multiple occurrences of an eigenvalue, lambda I, so that its algebraic multiplicity is more than 1. We have to look at its eigenvectors. Okay, so we have the eigenvalues, lambda I, of certain multiplicity. It could have the same eigenvectors, or it could have different eigenvectors. Even though the eigenvalue lambda 1 occurs 3 times, there could be 3 different corresponding eigenvectors, right? Or there could be 2 linearly independent eigenvectors, all these cases. So the geometric multiplicity of lambda I is the dimension of the span of the eigenvectors of V. Okay. So, in other words, the geometric multiplicity is the number of linearly independent eigenvectors Vi of lambda I. And the algebraic multiplicity is always greater than or equal to the geometric multiplicity. An example will make this clear. Okay. So mu of lambda I is always greater than or equal to gamma of lambda I, where gamma of lambda I is the geometric multiplicity. Here's an example. This is a matrix. What are its eigenvalues? Anyone?
2,
2, 1, because this is a triangular matrix. So P of lambda is lambda minus 2 squared times lambda minus 1. And using non-unique indexing, so lambda 1 equals 2, lambda 2 equals 1. What's the algebraic multiplicity of lambda 1? 2. And the algebraic multiplicity of lambda 2 is 1. So mu of lambda 1 equals 2, and mu of lambda 2 equals 1. Okay, now focus our attention on lambda 1 equals 2. We'll find the corresponding eigenvector. Okay. Let the eigenvector be A, B, and C. Whence we must solve A times V should be equal to 2, which is lambda 1 times V, which is P1, that is ABC. Whence A, B, and C must satisfy this. or B equals C equals 0. Negative 3C equals 0, so C equals 0. 3B minus 0 equals 0 when B equals 0. So B1, plugging 0 values for B and C, and we pick A equals 1 so that B1 is a unit vector. So V1 is 1, 0, 0. So lambda 1, we have only one eigenvector, V1 equals 1, 0, 0. Okay. And likewise, you can take lambda 2 equals 1 and find the corresponding eigenvector, which actually gives you this. You can try this separately. What are the geometric multiplicities? For lambda 1 equals 2, we have only one eigenvector, 1, 0, 0. So its geometric multiplicity is 1. The geometric multiplicity of lambda 2 equals 1 is also 1, which is the same as the algebraic multiplicity in lambda 2. But what about lambda 1? The algebraic multiplicity is 2, but the geometric multiplicity is 1. Okay. The geometric multiplicity will be less than equal to the algebraic multiplicity. Here's another example. A, and its characteristic polynomial turns out to be this. And if you solve, what's the algebraic multiplicity of lambda 1 equals 4? You see that lambda 1 equals 4, right? Its algebraic multiplicity is 2. Now, when we try to find the eigenvalue V1, we actually get 2, 1, 1, 0, 1, 0, negative 1. So for lambda 1, mu equals mu of lambda 1, the algebraic multiplicity is 2, and the geometric multiplicity is also 2. Here, the algebraic and geometric multiplicities of this eigenvalue are both 2, they're equal. And of course, lambda 2 is negative 2, and we can find the corresponding eigenvector 1, 1, 2. Its algebraic and geometric multiplicities are both 1. A defective matrix. So this is the characteristic polynomial. We are using non-unique indexing of the eigenvalues. Summation mu I should be equal to n. The algebraic multiplicity is always greater than equal to the geometric multiplicity. Okay. Mu of lambda I is always greater than equal to gamma of lambda I. Now, a defective matrix. If the algebraic multiplicity of any eigenvalue is more than its geometric multiplicity, then the matrix is defective. Otherwise, the matrix is non-defective. Okay. And everywhere in this course, we will be dealing with non-defective matrices. So the eigenvectors of an n by n non-defective real symmetric matrix span an n-dimensional space. If X is a point in n-dimensional space and A is a non-defective n by n matrix, then all these points Y will lie in an n-dimensional space, not in a subspace, not in a hyperplane of this n-dimensional space, but they'll be all over the n-dimensional space. Any questions?
No.
No.
So this is an example of a defective matrix. We had mu, this was the one of the examples we saw earlier, and lambda 1 equals 2. Its algebraic multiplicity is 2, and its geometric multiplicity is 1, right? And so we have the eigenvectors here are just 2, V1 and V2. So they can define a two-dimensional space, right? The span of V1 and V2 is a two-dimensional space, not 3 dimensions. Okay. So this is an example of a defective matrix. And this other matrix that we saw earlier is an example of a non-defective matrix. So we have 3 different vectors here. V1 has 2 values, 1, 1, 0, and 1, 0, -1, and V2 is 1, 1, 2. And they're all linearly independent, so they span a 3-dimensional vector space. Lemma. The determinant of a matrix is the product of its eigenvalues. Determinant of A is product of its eigenvalues. Proof: lambda I minus A equals this, right? By definition. I'm using unique indexes for the eigenvalues here. Now let lambda equal 0. When determinant of negative A is equal to this, correct?
Yes.
So -1, which is -1 to the n times the product of the eigenvalues. When negative determinant of negative A equals this, -1 to the power of n times the product of the eigenvalues. Whence the determinant of A itself will be, by the property of determinants, determinant of A is -1 to the power of n times the determinant of minus A. Okay, which is this, simply the product of the eigenvalues. So the determinant of the matrix is the product of its eigenvalues. Two more lemmas. The trace of a matrix is the sum of its eigenvalues. You remember what the trace of a matrix is? The sum of the diagonal elements. Okay, let's go back to this. Let's take this matrix here. What's the, or this one, what's the determinant of this matrix?
The
determinant of this matrix is lambda 1 is 4, right?
Yes.
So 4 times 4 times negative. What's the trace of this matrix?
6.
7 plus 1 plus 2. Absolute values.
Oh,
10, right?
10. Mm-hmm.
And so 4 plus 4 plus 2 is 10. Sorry, I forgot to mention, for the trace, we take the absolute values. Anyway, so the other lemma is the eigenvectors of 2 distinct eigenvalues are linearly independent, because we are dealing with non-defective matrices. So if lambda 1, if lambda I is not equal to lambda j, then Vi is not equal to Vj. Okay, this one we'll prove actually. Lemma: the eigenvalues of a Hermitian matrix are real. Because in general, when you solve the characteristic polynomial, you can get complex roots, right? A matrix can have complex eigenvalues. But a Hermitian matrix will only have real eigenvalues. And since we are, for the most part, confining our attention in this course to matrices with real scalar elements, it would be A transpose in that case. A conjugate will be A. Now, AV equals lambda V. First of all, we assume a Hermitian matrix. So let A be a Hermitian matrix so that A equals A star transpose. Now, by definition, AV equals lambda V. Hence, let me pre-multiply both sides with V star transpose. So, V star transpose AV equals lambda times V star transpose V. Since lambda is a scalar, I can move it to the left. Otherwise, remember, for vectors and matrices, the order of appearances must be preserved. So this is my equation 1. V star transpose AV equals lambda V star transpose V. Again, from the definition, AV equals lambda V. Let me apply the conjugate transposition on both sides. So AV star transpose equals lambda V star transpose. Hence, when I do the transposition, I must reverse the order of appearances. Hence, V star transpose times A star transpose equals lambda star. Lambda is a scalar, so lambda star transpose equals lambda star V star transpose. Now let me, okay, so this is what I have. Now let me post multiply both sides with V. Hence, V star transpose AV equals lambda star V star transpose V. This is my equation 2. Now compare equation 1 and equation 2. What do you see? The left-hand sides are both equal, right?
Yes.
And both are equal to the left-hand sides of both being equal to the same V star transpose AV, which means that right sides must be equal. So lambda V star transpose V must be equal to lambda star V star transpose V, correct? What's V star transpose V in both cases has to be non-zero because V is a non-zero vector, whence lambda must be equal to lambda star. So if lambda is equal to its complex conjugate, then its imaginary part must be 0, right? It must be a real quantity. Therefore, we conclude that lambda is real. Are you guys okay?
Yes.
Yes.
Therefore, lambda is real. Okay. So next lemma, the eigenvectors of a real symmetric non-defective matrix are mutually orthogonal. This is very important. Okay. When we do spectral decomposition, this will come into play. In other words, now you also know that we normally try to normalize the eigenvectors so that the Euclidean norms are all 1, right? So what that means is, since we are per this lemma, they're also orthogonal to one another. So if Vi so we have Vi and Vj are 2 eigenvectors, then their inner product Vi transpose Vj is equal to 0 when I is not equal to j. Okay, that means they're orthogonal. They're orthogonal if their inner product is equal to 0. In physics, this would be what would the inner product be? It would be the length of VI times the length of VJ times the cosine of the angle between them. If the cosine of the angle between them, if the angle is 90 degrees, then the cosine is 0, right? Hence, we get 0. Okay, so this is what we mean by VI and VJ being orthogonal. And of course, if I equals J, then we are looking at VI transpose VI, right? Which means this is the squared length of VI, the squared Euclidean norm of VI. And since VI is a unit vector, its squared length must be equal to 1. Okay, hence this is what the lemma actually says. VI transpose Vj equals 0 when I is not equal to j and 1 when I equals j. And this is equal to delta ij, where delta is the Kronecker delta function. This, by definition, delta ij is 1 when I equals j and 0 when I is not equal to j. This is a simple way to represent this. Proof. Let lambda ivi and lambda j be two eigenpairs with different eigenvalues, lambda I and lambda j. So vi is not equal to vj. So we are looking at two different eigenvectors, vi and vj. Okay, and we have to show that they are orthogonal to one another. In other words, we have to show that vi transpose vj should be equal to 0. Okay, now avj equals lambda j vj, correct? Pre-multiplying both sides with vi transpose avj equals lambda j vi transpose vj. That's my equation 1. Again, avi equals lambda I vi. Pre-multiplying both, this time I take the transpose of both. So avi transpose equals lambda I vi transpose, whence vi transpose a transpose equals lambda I vi transpose. But what is a transpose?
A.
Symmetric matrix. So this is A, right? Are you guys looking at the whole screen, or do you look? Are you looking at like something else, like with this block, something black? Which are you looking at?
I'm looking everything, all the screen.
Only the white screen, right? Like
Yeah.
Yeah, the presentation is visible.
the presentation is what? Excuse me, once again.
Yeah, sir, it is visible clearly.
Clear now?
Yeah.
Okay, so that's only with me because I'm administering the Zoom meeting. That's why. Anyways, so this is where we are. Vi transpose. I just took the transpose of both sides, and so this is what I have. And now let me post multiply both sides with Vj. Okay, first A transpose equals A, so I rewrite it in this manner, and then I post multiply both sides with Vj. Whence I have Vi transpose Avj equals lambda I Vi transpose Vj. That's my equation 2. Now compare the left-hand sides of equation 1 and equation 2. What do I have? They're equal, right?
Yes.
Vi transpose A Vj is what appears on the left-hand side of both expressions 1 and 2. Whence their right-hand sides must also be equal. Whence This was equation 1, this was equation 2, and therefore, from 1 and 2, the right-hand sides must be equal. Lambda j vi transpose vj should be equal to lambda I vi transpose vj. Vi transpose vj, we assume that lambda j is not equal to lambda I, right? Lambda j is not equal to lambda I. This was our assumption. So what can we infer? If lambda j is not equal to lambda I, but lambda j times this inner product is equal to lambda I times the same inner product, we can only conclude that Vi transpose Vj must be equal to 0, which means that Vi and Vj are orthogonal to one another. Oops. Correct?
Yes.
Yes.
This concludes proof of this lemma. Similarity transformation. Okay, suppose we have some non-similar matrix T, square, non-singular square matrix T, okay? And A and B are two matrices that are related as per this expression here. B equals T inverse AT. Then we say that matrices A and B are similar matrices. A is similar to B. And this is the similarity transformation from A to B. This is the operation that we do to transform A to B under this similarity transformation. Okay. So let B equals T inverse AB. Then for every eigenpair B, if lambda and B is an eigenpair of B, then lambda and TV is the corresponding eigenpair of A. So what happens under similarity transformation? The eigenvectors get transformed like this.
Good.
Eigenvalues, more importantly, the eigenvalues do not change under similarity transformation. So if we have two matrices, A and B, related as per this expression here, then they have the same eigenvalues. Proof.
Dr. Sorry.
What was that? Did I have a question?
Yeah, Doctor, what does it mean that A and B are similar?
This is the definition of similar. This is what we call a similarity transformation.
Oh, the T and T inverse? That is...
No. A and B are similar. A and B are two similar matrices. If we can define some matrix T such that B equals T inverse AT.
Okay, thank you.
So BV equals lambda V. Okay. We take this. BV equals lambda V. Whence T inverse ATV equals lambda V, right? Because B equals T inverse AT. Pre-multiplying both sides by T, what do we get? AT, T inverse, what's T times T inverse? Identity matrix, right? When ATV equals lambda TV, right? Another way of saying that is I bring this T on this side. So this T inverse, if I bring it here, it becomes T. So AT times V equals lambda TV, right?
Yes.
When A times TV equals lambda times TV. So TV and lambda, by definition, are an eigenvector and eigenvalue of A, right? So this shows that this lemma holds. Shifts. This is, by this we mean shifting the matrix A. So we have a matrix A minus sigma I for some scalar sigma gives us B. What we have done effectively is only the diagonal elements of A we subtract by the same amount sigma. Okay, so this is what is called by shifting. What happens here is the eigenvalues also shift by the same amount sigma, and the eigenvectors remain the same. So this is this lemma here. Let B equals A minus sigma I for some scalar sigma. For eigenpair lambda V of A, what will be the eigenpair of B? I just told you that the eigenvalues will shift. The eigenvectors won't be affected by the shift operation. So lambda minus sigma and V will be the corresponding eigenpair of B. So AV equals lambda V. We'll show this. When AV minus lambda V equals, AV minus sigma V equals lambda V minus sigma V. I'm just subtracting sigma V from both sides. Whence A minus sigma IV is equal to lambda V minus sigma V. Correct? Whence, by definition, if A minus sigma I is the matrix here, B, then its eigenvector and eigenvalue are lambda minus sigma and V. Correct?
Yes.
Yes.
So this is shifting. Eigenpair of inverse of a matrix. And I'm assuming that the matrix is invertible. Okay. If the matrix is non-invertible, then at least one of its eigenvalues must be 0. Its determinant must be 0, which means that at least one eigenvalue must be 0. So I'm considering an invertible matrix, a non-singular matrix. So the eigenpair of A inverse, so the eigenvalues you need to invert, but the eigenvectors will remain the same. AV equals lambda V. Okay, well, this is the proof. When pre-multiplying both sides with A inverse, we have A inverse AV equals lambda A inverse V. What's the left-hand side? V, right? A inverse A is the identity matrix. So V equals lambda A inverse V. Or rearranging this equation and dividing both sides by lambda, I am assuming that lambda is not equal to 0. So A inverse V is equal to lambda inverse, which is 1 over lambda times V. So by definition, this is A inverse A V equals lambda inverse V. So lambda inverse 1 over lambda, that is, and V are an eigenpair of A inverse. Okay. Quick recap. So AV equals lambda V is the definition of eigenvalues and eigenvectors, and by default we'll assume left eigenvalues and left eigenvectors. This is the definition of right eigenvalue, right eigenvectors. For lower triangular and upper triangular matrices, the eigenvalues are the diagonal elements. And our usual manner of representing eigenvectors is by normalizing them, so that the Euclidean norms are all equal. And we usually arrange the eigenvalues in descending order of their magnitudes. Lambda 1 is greater than absolute value of lambda 1 is greater than equal to absolute value of lambda 2, and so on. The spectral radius is the maximum of the absolute value. And the characteristic polynomial is the determinant of lambda I minus a, and it will have, we are using two forms here. This is unique indexing of the eigenvalues, and this is when we use non-unique indexing of the eigenvalues. Cayley-Hamilton theorem, actually I skipped this, so never mind. So this algebraic multiplicity is the number of times lambda I is the root of the characteristic polynomial. So it will be mu I, right? If you use non-unique indexing. So mu of lambda I is the algebraic multiplicity, which is simply equal to mu I. And the geometric multiplicity is the number of linearly independent eigenvectors. The geometric multiplicity is always less than equal to the algebraic multiplicity. For a non-defective matrix, for each eigenvalue lambda I, the geometric multiplicity and the algebraic multiplicities must be equal. The determinant of the matrix is the product of its eigenvalues. So if this matrix A is invertible, then none of the eigenvalues can be zero, right? Conversely, if this is a singular matrix A, then its determinant must be zero, which means that at least one of these lambda i's has to be equal to zero. Hermitian matrices have real eigenvalues, right? So, when we're dealing only with real numbers, then it means that symmetric matrices have real eigenvalues. Now, real symmetric non-defective matrix will have mutually orthogonal eigenvectors. Vi transpose Vj equals delta Ij. And then under similarity transformation, what happens? The eigenvectors change, but the eigenvalues remain the same. And when we do shifts, the eigenvectors are the same, but the eigenvalues also shift by the same amount, sigma. And what happens for inverses? The inverse, the eigenvalues will be inverted. The eigenvectors of the inverse of a matrix will remain the same. Any questions?
Nope, thank you.
Okay.
No.
No questions.
Okay. No questions? Oh. I don't know why it stopped. Okay, so we conclude today's lecture and we'll meet on Thursday.
Okay. Thank you, Dr.
Thank you.
You're welcome. Bye.
Bye.